Hello students, today we'll discuss IB Physics SL Paper 2, May 2018, Time Zone 2. My name is Neriman Melim. I'm located in Baku. Here you can see my mobile and email. Sources that you can use to prepare for exam. Main huge textbook from Oxford 2014, shorter textbook by Tim Kirk from Oxford 2014, and you should have two booklets from examiners. One, IB Physics Guide 2016, which describe exam syllabus and mention formulas, and second, physics data booklet, which include most of the formulas, about 95% of formulas, and this booklet will be available for you at the exam. So exam has 6 questions for 1 hour 15 minutes and 50 marks. Here we can see cover page of the exam. As you can see, calculate is required. Clean copy of physics data booklet with formula is required. Let's start. Question 1. A. A small ball of mass m is moving in a horizontal circle on the inside surface of a frictionless hemispherical ball. So the ball moves in a circle along this path. The normal reaction force makes an angle theta to the horizontal. State the direction of resultant force on the ball. So we have circle. Resultant force should be centripetal, directed to the center in the horizontal plane. So circular motion resultant is always to the center of the circle here in horizontal plane. Okay, next let us divide screen. Next question. On that diagram, construct an arrow of the correct length to represent the weight of the ball. So this is a picture. So this is ball, reaction, weight is directed downward, and it's finished here because resultant is exactly horizontal. So this horizontal. So we have, if you add reaction and weight, you will get resultant along the surface. So resultant force F. Shows that the magnitude of the net force on the ball is given by the following equation. So we sketch the picture. Reaction, weight, and centripetal force F. Weight equals mg. From this triangle we can see that F is linked to mg through theta. It is tangent. So if we divide mg by F, you'll get tangent. So F equals mg tangent. So this is what they asked. Done. The radius of the ball is 8 meters, 22 is the angle. Determine the speed of the ball. So first of all, I have redrawn the picture, and this is the radius of the circle along which the ball is moving. This radius is not the radius of the ball. They're linked, according to this picture, by the trigonometry. So small r by capital R equals cosine theta. So r equals r cosine theta. Now let us move to equation. First of all, centripetal force equals F. Centripetal force from section 6.1 of the booklet equal mv squared over r. R equals r capital cosine theta according to this picture. Now we work with this equation and we write substitution for each expression for each of the side, left side and right side. For left side we put mv over r. For right side, we put our answer from previous question, mg over tangent theta. We solve for v squared, then we make square root of both sides and substitute and give answer to two significant figures, because radius is 2 significant, angle is 2, so minimum is 2 significant figures. Outline whether this ball can move on a horizontal circular path of the radius equal to the radius of the ball. If it were moving, then we have reaction horizontal, weight vertical. So there is no component of reactions that balance the weight. So we cannot get circular motion, centripetal force. So weight will not be balanced as no vertical component of reaction force. Okay, next. Now we need to scroll the upper side. Read the question. Here we are, D. A second identical ball is placed at the bottom of the ball, and the first ball is displaced so that its height from the horizontal is equal to 8 meters. What happens next? The first ball is released and eventually strikes the second ball. The two balls remain in contact. Determine in meters the maximum height reached by these two balls. 3 points, but many steps. We are going to use energy and momentum consideration. So energy conservation at some moment and total momentum conservation at another moment. First ball has potential energy, which turns into kinetic energy before strike. All turns into kinetic energy before striking the second ball. So we can find the speed of first ball before the strike. So before collision, first ball potential energy turns into kinetic. Kinetic energy is mv squared over 2. Potential is mgh. Hence, v equals square root of 2 GH equals 12.52. Now they strike and they move together. Remember, if they stick and move together, kinetic energy is not conserved. Part of the energy here turns into heat, into deformation. But what is conserved? Total momentum. This is why we write expression total momentum before the strike and total momentum after the strike. Conservation of momentum. Momentum before equals momentum after. It means that mv before equals 2m, two masses move together with unknown velocity x. So this velocity appears to be v over 2 according to this equation, and we find the value. Okay, with 4 significant figures. After the strike, because we have frictionless surface, we have conservation of energy. So all kinetic energy turns into potential and two balls move up. Conservation of energy after collision. Potential equals kinetic. Potential before equals kinetic after. mgh in the end equals 2 masses x squared over 2, and finally we find that the height is 2 meters. 2.0 meters. Finished with this question. Question 2. Upper panel. An ideal monoatomic gas is kept in a container of volume so much, temperature so much, pressure so much. State what is meant by ideal gas. There is different approaches. The easiest is ideal gas obeys 3 ideal gas laws. Calculate the number of atoms in the gas. So volume, temperature, pressure are number of molecules should be found. Section 3.2, number of moles equals n over n Avogadro. Ideal gas equation is PV equals nRT. Substituting instead of n over n Avogadro, we have formula for number of molecules, and we find it with two significant figures. Calculate in joules the internal energy of gas. Section 3.2 of formula booklet. One molecule has energy 3/2 Boltzmann constant absolute temperature. We calculate it, and then we calculate by the number of molecules that we found before, 170 joules. The volume of a gas is increased to so much at constant pressure. Calculate in Pascal the new pressure of gas. 1 point. Boyle's law, product of pressure and volume, doesn't change. So this means that case 1 equals case 2. Pressure case 2 changed, and it is so much. So what happens to pressure? It decreased as volume increased. Explain in terms of molecular motion this change in pressure. As volume increased, speed didn't change, but molecules collide with walls less frequently, and hence pressure decreases as pressure equals F over A. Here you can put but. Right. Question 3. A loudspeaker emits sound towards, loudspeaker emits sounds towards the open end of a pipe. The other end is closed. A standing wave is formed in the pipe. The diagram represents the displacement of molecules of air in the pipe at an instant of time. Outline the standing wave. How the standing wave is formed. So the standing wave here is the result of superposition of two waves moving from the left from loudspeaker and reflected from the closed end moving to the right. So they move towards each other. One wave from loudspeaker, another from reflected from the closed end. X and Y represent the equilibrium position of two air molecules in the pipe. The arrow represents the velocity of the molecules at Y. Draw an arrow that represents the direction of motion of the molecule at X. So, as here molecules move to the right, here molecules will move to the left. Label position N in the that is a node of the standing wave. Okay, so all this we have done in here. So between nodes we have the same phase. So all of them here they move to the left, here they move to the right. Nodes. Let's mark nodes. So one node will be here. This point doesn't move at all. One node here, and another node will be here at the closed end. So one node, another node, and actually it's good to put here letter N. So letter N here and letter N here to label. So these are our two nodes. The speed of sound is so much, length of pipe is so much, calculate the frequency. Right. So distance between node and node is lambda over 2. It means that lambda over 2, this is lambda over 4 together, so or we can say that lambda over 2 equals 2/3 of L. Yeah, so from this we can find lambda. So from here to here lambda over 2, from here to here lambda over 4, lambda over 4 and lambda over 2, 3/4 over lambda, or lambda equals 4/3 of L. Wave equation is speed equals frequency times wavelength. We rearrange it for frequency and we substitute wavelength that we found and we get frequency 850 Hz. The loudspeaker, now we need another upper panel. First we close this part. We don't have it. Right. The loudspeaker, okay, let's close it. Right. Okay. Here we are. Right, the loudspeaker in A now emits sound towards the air-water boundary. A, B, C are parallel wavefronts emitted by loudspeakers. The parts of wavelengths A and B in water are not shown. Wavefront has not yet entered the water. The speed of sound in air is so much, in water so much. The wavefront makes an angle theta with the surface. Determine the maximum angle at which the sound can enter. Give your answer to the correct number of significant figures. When we go from air into water, the angle of refraction will be greater than angle of incidence, and at some point it will be equal to 90 degrees. After that, no sound can enter the water. So we use formulas for section 4.4. So ratio of speed equals ratio of sine angles. If angle in the second media is 90 degrees, sine becomes 1, and sine of angle, which is called critical angle, is here 13.1 degree. Draw lines on the diagram to complete wavefronts A and B for theta less than theta maximum or critical. So let's get rid of this panel. So first we draw direction that is towards this point. Then we know that direction will be away from normal. Normal is perpendicular, so away from normal will be like this. And these wavefronts always are at 90 degrees to the direction, so we draw one wavefront and we draw another. So we have sketched A and B in water. Question 4. The diagram shows a potential divider circuit used to measure EMF of a cell. Both cells have negligible internal resistance. State what is meant by EMF of a cell. So I took answers from Mark scheme. This is what examiner want to see. The work done per unit charge, 1 point, in moving charge from one terminal of cell to another around the circuit, another point. So just learn by heart this answer. AB has length 1 meter. Resistance of AB is 80 ohm. When length of AC is 0.35, the current in cell X is 0. Shows that resistance via AC is 28 ohm. So we have wire AB and part of this wire AC. From section 5.2 we have formula for resistivity, which can be rearranged for formula of resistance of piece of wire with length L and cross section A. So then we take ratios of two resistances, AC and AB, and they appear to be equal to ratio of lengths. As a result, we rearrange this formula, solve it for resistance AC part, and we get answer 28 ohms. So this is what they wanted. Done. Determine E. So let's consider right loop in which we have EMF and potential difference AC. They're equal. No other potential false because current is zero. So, but potential at AC is current through left loop multiplied by resistance. Current through left loop equals EMF by resistance, and it is 12 amperes multiplied by our resistance give us 4.2 volt. Next question. In a pump storage hydroelectric system, water storage stored in a dam of a depth 35 meter. So this is the water storage, and it has some potential energy. The water leaving the upper lake descends a vertical distance 110 meters and turns the turbine of generator before exciting into the lower lake. Water flows at rate so much per minute, density is so much. Estimate the specific energy of water in this storage system, giving approximate unit for your answer. So energy is specific energy is energy per 1 kilogram, so we should divide by mass. Let us consider this storage tank. So energy of this water equals to mgh, and we should take h average. So average from 110 to 144, mathematical average. So center of mass is at the height of 127. So we use this in our formula for mgh. We get mgh divided by m, we get gh, and h we take average height. So this is the answer. Shows that the average rate at which gravitational potential energy of the water decreases is 2.5 gigawatt. Change of energy will be change of mass multiplied by gh. So water flows away. We assume that height doesn't change dramatically, but mass changes dramatically. So we divide. So rate is change of time. So we divide both sides by time, and we get change of energy by time, so rate of change. So if we divide by time, right part, we get rate of change of mass, g, average height. Change of mass will be volume by density, and volume is how much flows, so much volume per minute. So time is 60 seconds. So volume for 60 seconds, mass for 60 seconds. We divide by 60, we know the rate. Then we put this rate into this formula for rate of decrease of energy, multiply by g and by average height. And we get about 2.5 gigawatt. The storage system produces so much of electric power, determine overall efficiency. Very easy question. Section 2.3, efficiency equals useful power out by total power in. We divide this value by previous value and get 72%. After the upper lake is emptied, it must be refilled with water from lower lake, and this requires energy. Suggest how the operators of this storage system can still make a profit. In the mark scheme they say that water is pumped back up at times when the price of electricity is low. Why? Because they talk about pump storage hydroelectric system. In most hydroelectric systems the water appears behind the dam according to water cycle, evaporation, then rain, but here we have pumped storage system. Last question about Rutherford experiment. Okay, question 6. Rutherford constructed a model of atom based on the result of alpha particle scattering experiment. Describe this model. So I used answer, this is standard question, and I use answers from mark scheme. Most of the mass of the atom is confined within a very small volume called nucleus. All positive charge is confined within, here you see most, but here you see all. All positive charge is confined within a very small volume called nucleus, and electrons orbit in a circular orbit around the nucleus. Rhodium decays into palladium by beta minus decay. The binding energy per nucleon of rhodium is so much, and that of palladium is so much. State what is meant by binding energy of the nucleus. The energy needed to separate the nucleons of, I will add here all the nucleons of a nucleus. Shows that the energy released in the beta decay is about 3 mega electron volt. Total binding energy we calculate, so we look to number of nucleons 106 multiplied by binding energy, so we have total energy of reassembling the nucleus into nucleons. Find the difference, and the difference appears to be 3 mega electron volt. Next question. Beta decay is described by the following incomplete Feynman diagram. Draw a label arrow to complete the Feynman diagram. Identify particle V. So you should remember that during beta minus decay we have antineutrino. Antineutrino is, so we draw arrow against time, so goes down, and the particle here is negative W boson, because here charge positive, 0, positive, here should be negative, negative, and 0. Paper is over. Thank you for your attention.